Good morning, good afternoon, good evening, depending on where you are. Happy to have you join us today as we talk about measuring reflective and directional surfaces. So let's go ahead and get started. Hopefully we'll have some great things to present to you to help you dealing with those particular things. So our agenda today is, first we're going to talk about surface characteristics. Obviously, we're talking about measuring color, but we're actually really here to talk about today about measuring color that might be affected or is affected by the characteristics of the surface that we are measuring. So we'll talk about a variety of different surfaces. Then we're going to talk about different instrument geometries, because the way that these instruments go about measuring these different surfaces has an impact on how well they can measure them, which leads us to our third point, how the instruments see or measure those various surfaces. And then, as Robert said, based on any questions you all may have, we will answer those at the end. So let's talk about surface characteristics. We're going to identify three basic different types of surfaces that present challenges or issues to doing color measurement. The first one, typically people consider to be gloss, but there are some other ways that we talk about it. Sheen is often used to describe that. Reflectivity, the technical term for this is first surface reflectance, essentially meaning light that's bouncing off of the surface that has nothing to do with its color, but everything to do with the surface itself. So we're going to call this a reflective surface. And the example I'll use is foil. And you can see here, this is a picture of foil, it's a foil substrate that gets printed on. It's a pretty much mirror-like surface. And purposely in the photo that I took, I made sure we can see where the light is. And so even though this is a solid piece of material, one consistent color, as you can see in the photo, it goes from everything from completely white to completely black, depending upon the how the reflectance of the light is seen by our eye or by the camera in this case. So that's one, the reflective surface. You can think of anybody who's working with metals, extremely high gloss. Sometimes in paint, there are people who will apply a clear coat over a paint to increase the gloss. And even an extremely glossy plastic piece, really any material that has extreme gloss will fall into this reflective surface category. And again, we're going to talk about how we manage and measure and deal with the idiosyncrasies of these different surfaces. So that's the first one. The second surface we want to talk about has directionality to it. Often this can be caused by machining or molding. It can even be grain if we're talking about a natural substance, stone, marble, wood, those kinds of things. And we call these, or in our presentation anyway, we're calling this a directional surface. An example I'm going to show is brushed aluminum. So it's got machining marks in it. You can see that it's not a homogeneous color, even as you scan from left to right across that photo. If you go from top to bottom, you can of course see it's a reflective directional surface, quite honestly. We can see it's got some gloss to it because we can see the light in it reflecting and causing it to be different colors as we move up and down the sample. But as you look across it left to right, you can see, it's got some direction to it. Like I say, brushed aluminum is a great example of this. So the third one is a bit different. We call them sometimes effect finishes. Some people call them a metallic color. They contain an aluminum flake or a pearlescent. These are, generically, we call them an effect surface. And an example of that is a metallic car paint. So this is a lovely red metallic paint. It's got some aluminum flake in it. I believe it also even has some pearlescent in it. In this picture, you can see the variation of the color across it. And of course, if you think about an automobile or something that's got this kind of a finish on it, the color changes as we change our viewing angle. So here, the surface is not only in the other two, it's more of a lightness shift, right? We see it going from very light to very dark, depending upon the angle of light and so forth. Here, with effect finishes, now we're actually changing color. The hue might change, the chroma might change as we change our angle. But all three of those kinds of surfaces that we're talking about today are affected by angle and light and can be a challenge to measure. So we're going to pop up a poll question here. And the first question we're going to ask you is if you measure any of these kinds of surfaces. And maybe there are others as well. And so if that's the case, go ahead and indicate that. Just helps us understand our audience to know the kinds of things that you might be measuring and are important to you. All right. Robert will leave that open for a bit for you, and I'm going to go ahead and move on. So let's talk then about instrument geometries, because they are a big part of what's the right instrument to choose. So we'll start with a 45-0 geometry. We're not going to spend a lot of time talking about these geometries. If you're interested, we actually did a webinar about a month ago specifically on geometries and went in depth on that. You can find more information about that on our website and actually get access to that, I believe. So briefly, a 45-0 geometry instrument is called that because the lamps or the light is coming to the surface at a 45-degree angle and the measurement is happening at 0. The key for us today when we're talking about surface and directionality is that the light coming to the sample in this case is columnated. In other words, those lamps aren't just shining onto the surface. There's literally a lens there that's focusing the light. Think of it like a spotlight or a flashlight where you've got a beam of light and you're focusing it at a specific angle. That's the way a 45-0 instrument illuminates the object to take its measurement. And it's used in a lot of places. We've got several different instruments that we manufacture that measure with this kind of geometry. And they are very successful, again, knowing what kinds of surfaces we'll be measuring. Contrast that with what's called a sphere geometry, or D8. Just like in a 45-0, the first part of the designation is where the light's coming from. So for a sphere, we get a letter, not a number. So the D means that it's a diffuse illumination. So the way that a sphere instrument works is, again, we have a light, but instead of having a lens that's giving me columnated light, focused beam of light on the sample, the light is shining on the inside of this sphere, which is a white, very reflective, very diffuse surface. And so each beam of light that comes off of this lamp and hits the wall of the sphere bounces in every direction. And so essentially we end up with this sphere, this hollow globe, if you will, reflecting light down to the sample at every direction. So diffuse light, much more like what you would experience in the room you're sitting in, most likely. You might have some direct light, but for the most part, if you're like in a place like my office, there's overhead lighting that has diffusers on it to try and make it so you don't have shadows, but everything is lit evenly. Okay, so that's the way that the sphere geometry instrument does its measurement, is with a diffuse light. And again, we have benchtop handheld versions of this geometry in various instruments that can measure that way. Finally, we talk about something called a multi-angle geometry, and it's specifically designed, and you'll see when we talk about effect finishes, because it's designed to measure color at more than one angle. So this instrument, like a 45-0 instrument, has a lamp with a lens that's focusing light at a specific angle. It's at 45 degrees to perpendicular for the sample. So it's essentially presenting light to the sample exactly the same way a 45-0 instrument does. But what it does is instead of just measuring at one spot, what's labeled 45 degrees here, perpendicular to surface, it's also measuring at, in this particular example, total of five angles. We have instruments that will go all the way to 12 angles of data to capture how the color is changing depending upon viewing angle. So two instruments, the 45-0 and the multi-angle, that use focused columnated directional light, and one instrument type, the sphere, which uses diffuse illumination. And there's a photo of the multi-angle instrument. So Robert's going to pop up another poll question for you, just asking if you're already using instrumentation, if you know, what type are you using, all right? Are you using a 45-0? Some of you may have an instrument and say, well, mine is a 045. Those are essentially the same devices. 45-0 or 045 instruments are identical in the data they produce, sphere or multi-angle. So go ahead and let us know that. Again, that helps us understand the audience a little better. All right, so now we're going to move on to the real crux of this. We understand a bit about the different kinds of surfaces. We understand a bit about the different kinds of instruments that we could use to measure those surfaces. Let's talk about how those different instruments see those different surfaces. In other words, let's choose the right tool for the job. And just like a screwdriver has modern screwdriver may have multiple interchangeable heads we can put in it to do different things. Instruments, color measurement devices, spectrophotometers, they all measure color, but they're designed for specific uses. So let's start with the reflective surface. So we're, again, looking at our foil. And the way we're going to do this is I'm going to actually show you. Here we have the 45-0 instrument. And I'm just sharing LAB data, right? L being an indication of lightness, A being red or green, B being yellow, blue. And the spot you see over on the right where it says 45-0 foil is actually a rendering, if you will, that our software will do of those LAB values. So in essence, it's saying a 45-0 sees that foil as black or nearly black, right? The L value is 18. That's pretty low. The A and the B are both fairly close to 0, which means it's really neutral, right? It's not, doesn't have a reddish cast or a greenish cast or anything to it. It's a pretty neutral, pretty close to black color if I measure it with a 45-0. If I measure the same exact spot, and by the way, when I did these measurements, that's exactly what I did. The spots of the samples were identified so that in each case we're always measuring the exact same place to eliminate any variation that might exist within the sample. So with a sphere, it's seeing it as a gray. It's a pretty dark gray, but you can see there's a significant difference in the L value. And why is that important? Well, if I'm trying to compare two pieces of foil to each other and I measure them with a 45-0, because it's so close to being black, any color differences that my eye might see are going to be minimized because the instrument is essentially blinded by the reflectivity of the surface. In other words, think about the 45-0 light. The light comes at a 45, and it's going to bounce away almost all of it at the opposite 45-degree angle, leaving very little light to come to the sensor. And so what we experience is if you have two pieces of foil or two very reflective surfaces that look different, the 45-0 instrument may not measure them as different as you see them, where the sphere, because it's a diffuse illumination, more closely agrees with what you will see with your eye. And that's really what we're after, because an instrument, if it doesn't mimic human vision, doesn't really help us a whole lot, because our customers all make purchasing decisions by looking at things. They don't walk around with spectros in their pocket. All right, so that's the reflective surface. Now we're going to move on to the directional surface. Again, this is a piece of brushed aluminum marked so that we're measuring a very specific spot. And you can see with a 45-0, I got a much higher L value here because it's not as glossy, right, as the foil was. So it's getting more light coming back, and it sees it as a gray, right? It can't see the variation in the color. Of course, it sees it as a solid gray. And again, A and B, it's really, really neutral. And 65 is a pretty decent lightness value. So we would probably be very happy to take that instrument, compare multiple things, and get a repeatable or a measurement that agrees with human vision. If I measure the sphere with the, if I measure the brushed aluminum with the sphere, again, I get a very neutral color. A and B are near 0. And it's lighter. It's seeing it lighter than the 45-0 is, again, because of the diffuse illumination. So at this point, you might look at those and think, and we might think either of these would be sufficient to do measurement of this. But then we've got another factor to consider. So with that spot marked on the brushed aluminum, I did some rotations. So imagine I measured the one spot as my standard, right? I then rotated the sphere instrument 10 degrees. So I'm still measuring the same exact spot, but I'm turning the instrument slightly, or turning the sample slightly, to move it 10 degrees from where I started in rotation. And the delta E there, you can see, is 0.22. And so I did 5 rotations at 10 degrees, 20, 30, 45, and 90 degrees. All of those measurements are within 1 delta E. Pretty repeatable, meaning I should get good correlation with visual, because I'm not subjected to an issue with the rotation. So before I show you what we got with 45-0, we're going to ask you one more poll question. And this one hopefully is a little more fun than just what are you using, what are you measuring. So we're asking you, when I do this exact same experiment of rotations with a 45-0, what kind of difference do you expect that you will see? So I'm going to give you just a few more seconds to give that some thought, give us an answer, and then I'm going to go ahead and show you the answer. I've probably set it up and you're all going to get it right, but that's okay. So here we go. The delta E, when I rotate the sample with a 45-0, as you can see, simply a 10-degree rotation created a 10 delta E color difference. What's interesting is when I go to 20 degrees, it gets a little closer. 30 degrees, it goes a little higher. 45, it's way out. 90, it's very different. By the way, I did a lot more measurements, and I can eventually, as I slowly rotate, eventually you find one where it tends to agree pretty well with the standard. You'll get some that are as much as 20 delta E away. So why is that? Well, it's the fact that I'm measuring a directional surface with a directional light source. And so the orientation of the sample to the instrument, as soon as I change that, I'm now measuring a different color, essentially, because if we think of a directional surface, essentially it has microscopic hills and valleys. And so there's going to be shadows that occur when I use a directional light source. And as I change the rotation of the instrument, the shadows become more or less, and they cause color variation. In most of these measurements with the rotation, the L value is the thing that's changing the most. A and B are not changing a lot on this particular sample, but there's lots of shift in L as we get more or less shadowing, more or less reflective areas, and so forth. So you can see there's some concern there, obviously, in using a 45-0 instrument to measure a truly directional surface, and we're talking about the physical surface having directionality in it. All right, so then let's move on to the last, the effect finish. And so I can measure it with 45-0 and get LAB values. You'll see the L is almost the same as it was when I measured the foil, but now I've got some significant A and B to it, making this a red, right, very deep red kind of color. Honestly, when I measure it with a sphere, I get very similar results, right? If you were to calculate the delta between those two, it's only a few delta E. They're fairly close to one another. The issue is that both of these instruments are essentially going to capture that color from a single angle. When I bring in a multi-angle instrument and I measure 5 different angles, right, you can see in the color representation on the right, that color looks very different at those different angles. And you can see the LAB values are very different. We've got a, 26 unit swing in L value and a 24 unit swing in the A value and an 11 unit swing in the B value, just based on what angle I'm at. So if I'm producing this metallic color specifically to achieve that, then I probably want to be able to measure those various angles, tolerance around them, monitor them, and control them as best I can. That being said, there are some metallic colors where it's going to have those effects, but they aren't critical to me. And so just a 45-0 measurement would be sufficient. And what's really interesting is if we look at the data for the 45-0 instrument and compare it to the 45-degree angle of the multi-angle, you'll see that those measurements are very close to each other. So the 45-0 does a really good job of presenting to me that one angle of data about that color. It's that if I need to be able to control what some people call the flop or the color shift that's happening depending on angle, a multi-angle instrument may be required. So to summarize, if we're going to measure any of these reflective or directional surfaces, number one, we need to understand the different geometries, tools that are available to perform these measurements. We want to ensure that the chosen tool provides measurements that agree with visual perception, and this can take some trials, honestly. If you've got surfaces that you think may be causing issues for you, and you have a particular kind of instrument you're using to measure them, you can do some pretty simple testing, similar to what I did. The directional one seems to be the one that is the biggest catch. If you've got a reflective surface, you're probably pretty aware of that. But the directional ones are sometimes causing issues of my numbers from my instrument don't agree with what I see visually. So the simple test, of course, is to mark a spot and simply rotate the instrument around that spot and take some measurements of it to see am I getting variation. There are some surfaces, by the way, that are so directional that even the sphere instrument sees some significant shifting. In other words, if I rotate the sample, there's enough difference that I can go from being in tolerance to out of tolerance. And in those cases, it may be a requirement that you've got to specify then how you're measuring that sample, right? Specify the geometry of the instrument and maybe even specify the orientation of the instrument to the sample so that one person isn't measuring it in one orientation and somebody else has got the sample rotated 90 degrees and measuring it, and they're getting differences that aren't the way that it should be compared. An example of that is in the automotive industry. They're always conscious about how they align the instrument with a multi-angle instrument to the sample being measured so that we aren't introducing color differences because of our measurement techniques. So specifying the geometry of an instrument, really important anytime we're communicating or sharing that color data.